Hey boys and girls, today is motor day, and what we're going to do is we're going to start off with the inverter. This is one of the motors off the Tesla Model S Plaid. This is the inverter. Let's take this off and let's look at this. This, like the sign says, is the Model 3 front. This is the Model Y front. This is the Model 3 rear. And this is the Model Y rear. Now, for those of you who aren't engineers, this is good engineering. This is forward and backward compatible. This is what I like to see when I see products manufactured and designed and put in the hands of the people who are going to basically live with this, because quite frankly, every one of them can take the same inverter package. This, by the way, I'm going to show you right now, has a little note on it. As soon as I find it, right there. Model 3. The other ones will say Model 3 as well, because this is the standard that they have inside their organization. And because this board is so advanced, it's going to be around for a long time. All they have to do is modify some of these chips, but at the end of the day, this is a really good design. Let's go and look at the rest of the motor. So before we get started, let's zero in on this a little bit. This is the board that came off of the Model Y. You'll notice that the insignia where it says Model 3 right there is in a different location. The Model 3 board and the Model Y board are very similar. Only a few components change. If we look at the difference between what we saw over on the other inverter versus this inverter, you can see that there are things that are in different locations, but a lot of it looks identical. To the average person, like you can see there's a couple of capacitors there that aren't here. These boards are very similar, and they're made to be modified a little bit so that Tesla can upgrade over the time that the product will be in the marketplace. And if you look, you can see this is one of the other inverters, and you can see that apart from, oops, wrong one. This is one of the other inverters that's from the Plaid, and you can see that they're identical. These are identical. Regardless of whether it's a front motor, a rear motor, it doesn't matter, it's identical. So with that, let's talk a little bit about the motors and the casings themselves. So Ben's with me, so I don't screw up, and we're going to talk a little bit about the integration of these two motors, and we've got them sitting right in front of us. Ben, why don't you jump in and
all right, I can do that. Thanks,
out.
Sandy.
Yeah.
So we have the rear motor assembly that's sitting at the front side of the table right now. They have two motors and two inverters that are all connected into one housing assembly. So when it gets mounted into the vehicle, it's going in as one unit. The gearbox housing has been integrated into the stator housing so that this is now one piece. They share a common gearbox housing on the inner side, which allows them to make this a very compact unit. There are two different oil pumps on the two different stators to keep both of them cool. Then there's another oil pump that's located in this middle center casting.
what we can do here is maybe show off the filter, the cooler, and one of those pumps in here.
This is the front motor that we've taken out. We have the oil filter, which there is just one oil filter on the rear 2 motor assembly as well. So one oil filter up front. They have one heat pump and then the heat exchanger. I said heat pump, I meant oil pump, I'm sorry. They have one oil pump up front and one heat exchanger. So each motor on the rear has the same pump and the same heat exchanger.
You know, one of the things that we noticed that we really like is if we look at the way the housing is put together, you've got a bolt that comes in from this direction, passes through that section, and then bolts into the rear housing for the stator. This is a really good way of making things happen, because in order to make bolts work really well, you have to torque them and then put them into yield. So you actually stretch the bolt so it turns into a spring. This arrangement here, having everything coming through in one direction and not having a bolt coming here and then tying into that center section, or from there and into the center section, that's a really good idea. Bolt stretch is really important, especially on aluminum products. So we were really happy to see what's going on with that.
Yep, and one other thing that they did integrate here is they don't have a differential on the rear. They have the 2 motors, so they're doing torque vectoring. Each motor is driving one of the rear wheels. It's not like the front where there is a differential in here, so that they're able to drive both of the wheels and you don't get any skid when you're going around the corner, any chirping of your wheels. Mm-hmm. They are using the same oil in these that they were using in the 3 and Y as well. So it's going down their production line. They don't have something else they have to pump into these. It's getting the same oil. And then they did change the gear ratio on these. They've lowered them a little bit. The Model S has a 7.54 to 1 gear ratio, when the Model Y, it was at 8.996 to 1. So it's been reduced quite a bit.
So let's look at one other thing that I was surprised to see, happily surprised to see, and that's over here. Here,
yep,
let me take
Sandy.
that. Yeah, I just didn't want to run over the tools here. There we are. This right here is a mirror finish. There are a lot of ways of making that happen, but the best way is something called roller burnishing, and that's what I think is going on here. Now this is where the bearings fit, and bearings have to have a very accurate and precise hole to be pushed into. This roller burnishing is, if that's what it is, and I think it is, this is a fabulous way of putting bearings into a housing. This will give me a dead accurate diameter to shove those bearings in, and the bearings like it when they're pressed in, and they want to be just the right snugness in order to make this work. This is something I haven't seen. Usually the only time you see this is like in brake components, like the master cylinder is done using roller burnishes, because it compresses all of the tool marks and whatnot, flattens it out, and makes it so that it's actually forged, cold forged, to give you this surface. And it's really, really something. I really, really am impressed with this. So,
all right, we'll take a look at a couple of other things that we have here in the housing. We're going to look where the inverter mounts into the housing next. So we have this cast-in feature here. That is for the bleed resistor that is on the inverter. So that's a heat sink. So it's using some of the cooling that's inside the motor that's cooling the stator to help cool the inverter as well. And then one other thing that they've done with this unit that Tesla hasn't done before is they are now side mounting their inverter, which means you have the stator that's right here. Typically they mount on the end of this on kind of a cap, but because of their width constraints, because they have 2 motors that are next to each other, they've had to move their inverter to the side. And one of the penalties from that, you can see this piece here is still in. That is where the inverter will connect to this bus bar, And this bus bar, this is the other side, so it's not going to sit in here the same way, but this bus bar is going to go and connect to your stator. The leads that they have on their stator typically connect straight to their inverter when you're able to end mount the inverter. So they've had to add a piece, but they kept the same inverter and the same inverter housing. So it is, it's a decision that they made to keep a common component that's complex and just bring in a simple bus bar.
The one thing we also noticed was the gasketing. There's no RTV on anything for this product. All of them are laminated gaskets. So these are gaskets these are the premium gaskets. You'll notice that they've got both a metallic part, in this case aluminum, and then gasketing material and an O-ring type of gasket, or a half O-ring kind of gasket that's molded on top. We used to call this vulcanized in place. I'm not sure what they're calling it now, but this is, like I say, the premium way of doing it. And the reason for that is because when I screw these bolts together, I want to have them into yield. That means that there's tremendous amount of force. If I use an ordinary gasketing material, it's going to flatten it out. With this, I will flatten the gasketing material, but this is going to act as a little bit of a shim to make sure that I don't crush it too much, so that it becomes ineffective. If you flatten just an ordinary seal, it'll leak eventually. So this is a really good gasket, really kind of expensive, but a very good gasket for the life of the product. This is like your million-mile kind of gasket.
Okay, and then we're going to jump onto the stator to talk a little bit next. The stators that they're using are the same ones out of the Model Y. Again, Tesla has gone with reusing components everywhere that they can. So this is something that they're taking, and they're already producing hundreds of thousands a year, and they're putting them into this vehicle. It's a coil wound stator, as you can see. It's a three-phase stator. They are, again, cooling through the channels in their laminates that are here. And they are using paper slot liners on the inside. Again, very similar, or the very same thing as the Model Y. So it's things we've seen before. And then they have a cooling ring that goes on top of this. So this is where the oil would be pumped through to go through the channels in here to help cool the stator. The same design and same architecture that they've had in their Model 3 and Model Y motors. All right, and then this stator, when it goes to get pressed in, they heat press this into place. So they will cool the stator some. They'll heat up the aluminum housing so the aluminum grows. This will shrink a little bit, put it in place. Then when they go to the same temperature, it's a very tight fit. To be able to get these out, we have to cut the stator housing. So it's effectively held in place without any fasteners. It's not gonna go anywhere.
So right now, what we see here is the standard wound type of stator. However, at the end of the program, we're going to talk or show you a little bit of something that we got from someone. I don't know who, but somebody sent us a little picture. And this is a totally different departure, or a departure from the standard way that Tesla's been doing things. And we'll give you a sneak peek at that right at the end of the program. So now we've gotten through basically the housings, the inverter, the stator, the cooling systems and whatnot. Let's move over here to the rotor. And I think the first thing that I want to do is give you an idea of something that really surprised me. This is the rotor, and you can see that it's got a wrap on it. The wrap is made out of carbon fiber, and this is what we would call a winding. It is just a bobbin basically, and it gets covered with carbon fiber and epoxy. It's a pre-preg, I'm sure, and when it's done, it's done. Now, That's something we've never seen before, and that's kind of amazing. But then we put the green paper on here, and that is not what I was expecting to see. If you remember before, I was telling you that all of the different laminates are slightly skewed so that you don't get pulsing. This one is doing something magic. This is not skewed. This is inline, and I've driven that car quite a bit, and I detected no pulse whatsoever. I'm astounded, I guess would be the right word. I've never seen anything like this before on a high-speed, high-power motor, and I think it's because Tesla's invented some new physics or something. The one thing on here that I would suggest, because I look at this and this would not be my first choice. I like the idea of the carbon fiber, but I don't like the winding. But we worked with a company that made the machines that make sweaters, socks, dresses, and that machine could knit a winding. If I was Tesla, I think I'd probably go with that, because I could take that carbon fiber, then I could slide it over. This will give you unidirectional, this works only in one direction. Whereas if I had a knitted or a woven blanket that goes over the top of this, I would get a lot stronger, a much, much stronger component. So I like the idea of this being carbon fiber, but I think that there's a better way to get the job done. The next thing that's kind of interesting is the laminates themselves. Now, I've never seen anything that looks like that, and these components here are a little different. You can see the magnets go in between here, and then you've got an end cap that holds it in place. Then you wind it with the carbon fiber. I've never seen anything like this before, and so consequently, what you're looking at here is, here's your laminates on the shaft. Here's the magnets. By the way, these magnets were all glued together. They don't come in little sections like this. They come in a long bar. And this long bar goes into the laminates, and basically they're held by these little cleats. See these little tiny cleats here? That's what holds it in place. Now the standard way of making a laminate case, or the traditional way that they've been using, is by using mechanical stapling. And you can see the little dimples here on this side and the little projections on this side. And that's kind of like stapling them together to make like a solid component. And that solid component, even though it's a whole bunch of, how many laminates did you say there was?
There are 529 laminates in each motor.
And that's a lot. So the statistics the statistics on this are a little bit different than what we've seen in the past. I've never seen anything quite like this. We know that what they're going to do is they're going to press on the laminates in one lump, and then they're going to take these long magnets, but they're not magnetized yet. But anyway, they'll take these long magnets and put them in place. I'm not sure how they do what they do to make this work because they don't touch. But maybe what they do is magnetize these and then drop these in place. I'm not sure. All I know is that what we're looking in the way of Gauss equipment, or sorry, the Gauss of this is phenomenal in comparison to the Model 3 or the Model Y. And we're just finding out now. So Ben is finding out how sticky the magnets are. So anyway, I'm going to turn it over to him. So, so anyway, why don't you fill us in on...
All right, so we'll take another look at what Sandy was just looking at here with this rotor that we've partially put back together. So we have two magnets in here. We have our inner laminates that we've built in, and then we've got these bridges that go on the top. We're just going to put this in so you can kind of see what it looks like when it's all together. Hopefully these stay kind of close to each other so we can show you what's here. And we'll pull the laminates apart a little bit. My tool gets stuck as well. But you can see that these are in here. They don't touch on the outside here, so they've removed that bridge that is on a normal laminate stack, and that has allowed them to get much better power and torque from this rotor. So they've patented this, and they're claiming in the patent that they're actually getting a 25% increase in peak torque and peak power because of building their laminate stack this way and using these pieces to remove the bridge that was here. So that's, then they've also, these magnets, we said it during the Mach-E video, but these magnets are super strong again. So we're gonna do a test. We've grabbed some of our different magnets here in a little bit. We're gonna walk to the back and do a pull test to see how strong these magnets actually are. Give you guys some numbers more than just us saying this is really strong. So we'll be doing that in a second. And then, is there any...
Actually, yeah, while we're on this, Corey wants me to do the big sale. So,
all right.
Anyhow, we have a very limited number of these laminates, obviously. And what we're going to do is we're going to be selling these. They'll be online. And like I said, these are really unique. I'm expecting that there's going to be a few people from the OEMs and people who make magnets that, or sorry, motors, I should say, that are going to be interested in the laminates and maybe the keepers as well. But at the end of the day, these will be up for sale shortly. I'm not in charge of any of that stuff. All I can tell you is that Corey wants me to let everybody know that we're going to be selling these. Whoops. And now, what are we on to next?
Now we are going to hop back over to the inverter. And something that is new in this inverter, Sandy showed you kind of the highlights before, but there is now a explosive charge with a couple of plungers here that are used to break these bus bars. So we're going to go through, we're going to set this up. We've rigged up test equipment, and we're going to run this to see what it looks like. So we will be setting that up right now. You can see this is out of the Model Y. The change in the bus bars, these were solid bus bars on the outside. The Model S, if you come over, you can see that they have been shaped to allow them to break. And so that will break, this plunger will break the inner piece of the bus bar, and then there is a fuse that connects the outer part. So this fuse will pop once all the power is being ran through the outer portion. So this is a third, fourth, fifth fail-safe that Tesla has installed to be able to cut power to the motors. They have different safety features inside the battery management system. Now they're adding another step in the inverter to physically cut power in whatever situation they need to do that in. So we're going to set this up. We're going to set up some cameras, and we'll hop behind the wall and we'll pop this and see how it goes.
Stay tuned. Okay, so we're almost ready to try this out. These types of explosive fuses are a little more exciting than just having something turn black. So we're going to ignite this, and you're going to get a chance to see it, but not with anybody else in the picture. Certainly not me, anyway. And you'll see that I've got the stator sitting on top of it. That's there for a reason. We're pretty sure that this is going to pop around, so I'm going to get out of the way. Anyway, here it comes.
3, 2, 1.
Oh, that was a big nothing. Ah, oh, you're kidding. I was hoping for a lot more than that. Oh, but you can see how this thing is blown out, and you can see it's basically broken broken the, what do you call it, the bridge. So I thought it'd be a lot more dramatic. We didn't need this. Could have just let it sit on the table, which is probably a good idea because I don't want to have a lot of stuff ruined on the circuit board. If there was some kind of accident or something, I guess I'd want to be able to identify what's gone right and wrong, at least maybe on that board. So this is kind of a cool idea, but it's a lot less than what I was anticipating as far as power is concerned. Yep, so anyway, there you go. And now Ben is going to talk to you a little bit about pulling, lifting magnets with, or lifting weights with magnets. Anyway, stay tuned for that.
All right, so we've completed all of our magnet testing. I'm going to walk you guys through how we did that real quick here, and then we'll show you some results. So what we have is a force gauge that we used. We mocked up a bolt on a wire so that we can pull. This is what's going to stick to the magnet. We're going to pull this off of the magnet. We took another large piece of steel that we have, which is our forklift tine. We marked an area here. We put the magnet on it so we can use the same piece of the forklift each time. And all we did was take the bolt, connect it to the magnet, and then we turned on our gauge. We used our peak value, put it in the loop, and we pulled it off. So this would have came out at 140 newtons of force. So we did this 10 times for each of the magnets. We used the BMW i3. We chose that one because that was the first electric vehicle motor that we have in-house, so it's the oldest one that we have. We used a Tesla Model Y. We also did the Mach-E rear motor as well as the Model S. And as you can see, the Model S does have the strongest force to pull this bolt off of the magnet. And that's just what we mean by this is a strong magnet. It's just a very anecdotal test as we get anecdotal feelings. We do send all of these magnets out to get their Gauss ratings, and that is available in our motor reports. And that's more what kind of number you would use if you're designing a magnet, designing a motor.
Okay, well, that's our little motor demonstration here. Thanks for watching. Stay tuned for Corey's announcement on how much those laminates will go for. And stay tuned. We're going to show you quite a bit more. This car is full of surprises. Thanks for watching again. Bye now.